Yep. It's all good, Debbie? What? No.
All right. Do we have everybody here? We don't need that one. I'll get that one for the other stuff. I have one that will show. I'll get you your forms in just a second. It's my great pleasure to introduce somebody who I think everybody here knows, but for posterity's sake anyway, Deepak, who's been a longtime member of the department, is now coming to the final stages of defense of his dissertation and is a successful effort and has pulled together an excellent work. I think you have a publication coming up on this work now?
Yeah, one is submitted, other is in prep, and one in co-discipline. There is a book chapter which is also in press.
Yes, excellent. So there's been a number of products has come out of this work, and we're looking forward to hearing about the research. So, and I think we have all of our committee members are online. The other two committee members are online, and this is being so for Dr. Ruta, who's going to be able to see it because it's I think 2 a.m. right now.
Yeah.
So, we'll get her input on it later. So the basic procedure that we'll follow, Dio is going to give a presentation. I think the length that we're estimating about 45 minutes or so.
Yep.
And then we'll have time for open questions from the audience. After we get open questions from the audience, to whatever extent we are able to extract good questions from everybody, then we'll dismiss the audience and leave it to the committee, both those online and present, to then grill Dio until he's done. And after which we'll dismiss you for a little while. We'll have our internal debate and then invite you back in with our decision. Any questions or concerns before we get started? Great. Okay. So without further ado, Dio, please take it away.
Thank you, Professor Rulis, for the nice introduction, and welcome all the committee members who are joining online and in person, and all my fellow friends, students, and families who are here. So yeah, I'm here to talk about my dissertation research, and my research is on recently quenched elliptical galaxies. I investigated quenching in them, and that's what I will be talking about here. But since I'm in a interdisciplinary PhD program, so I also have a co-discipline called curriculum and instruction. So about 20% of the talk would be about my co-discipline research as well, because I have done some significant work in that area too. So let's start with the astronomy stuff. But first, as my title says, I'm studying quenching via H1 studies in recently quenched elliptical galaxies. Before I dive in deep, let's understand what these words mean. H1, quenching, recently quenched elliptical, what are those? H1, in astronomy, if I say H1, it means hydrogen atom, or atomic hydrogen, or hydrogen gas, or cold gas. So from now on, whenever I'm talking about H1, sometimes I will be saying H1, sometimes hydrogen gas, sometimes cold gas. It all means the same thing. And it's the most abundant element in the universe, and also the raw fuel required to form stars. Now quenching, what is quenching? Again, in astronomy, quenching means star formation has stopped in galaxies. So, and it's also a key phase of galaxy evolution. Galaxies, when they transition from alive phase to dead phase, they go via phase of quenching. And what alive galaxies are, those who are forming stars. Dead, those are not forming stars. And alive galaxies typically would look like these spiral galaxies. And these spirals are the reason where stars are being formed actively. And quenched galaxy would look like a blob or elliptical reddish in color. So quenching is also a key phase which kind of not just changes the star formation activity, but also morphology. And even through the spectra also, we can say we can talk about the difference between these two galaxies. In star forming galaxies, the spectra the H alpha spectra, which is responsible for star formation activity, will be very much strong and significant. And in dead ones, you hardly see anything. So that's one of the difference between the spectra of these two galaxies. So now we have talked about what is H1, what is quenching. So what does recently quenched elliptical galaxy mean? As the name suggests, it's an elliptical galaxy, and it has been quenched recently, that is star-forming stars recently in past 1 billion years, which is small time when it in terms of galaxy's age. So now we have already covered some of the keywords. Now the next question to ask is, or the big question of my research is, why study quenching in them? What is so special about these galaxies? Well, we found that 90% of these RQEs resides in low density environment as the central galaxy. Central galaxy is the most massive galaxy of a group or a cluster. But why is that still a factor that we are considering in our study? Well, most of the galaxies either reside in low density environment or high density environment. Low density environment would be galaxies 10 or less, or isolated galaxies, and is an environment where star formation happens actively. It's a conducive environment. High density environment like clusters, it's not a conducive environment for star formation. So we see that these RQEs are in low density environment yet quenched. So the next question to ask is, why are they quenched then? Next thing would be to, as I mentioned, H1 is the raw fuel for star formation. So probably we can ask next question is, can you find some clues about quenching if we study the H1 content of these galaxies? And that's what we did. Yes, because quenching and H1 are related. How they are related? Quenching of star formation can happen in primarily 3 ways: by heating of the cold H1 gas, or by the ejection of the cold H1 gas, or by exhaustion of cold H1 gas. So there are different physical processes which can heat the gas in the galaxy, and that can stop the star formation. So there are key properties we need for star formation. Gas has to be cold, like really cold, 20 Kelvin, and the gas has to be dense enough. So, and the other properties of the gas, like if the gas is, because of some physical mechanism, has been ejected out of the galaxy, then there is no gas left to form stars. And exhaustion is you just ate all the gas or consumed all the gas in forming stars. Because of that also, star formation will stop. So recently quenched elliptical galaxy is my main concern that I'm studying here, but we included some comparable subpopulations as well in our study, which are plausible precursors to RQEs, we are calling it pre-RQEs, and plausible descendant to RQEs, calling it as post-RQEs. So pre-RQEs are exactly like RQEs in all properties except for the star formation activity. That is, they're actively forming stars and eventually evolving into RQEs. And post-RQEs are long dead, they have not been forming stars for a long time, and they are, if RQEs have been, basically RQEs old enough after a few billion years will be a post-RQE. So why use these comparable subpopulations in our study? Well, if the evolution has happened from pre-RQEs to RQEs to post-RQEs, then we can say by comparing their H1 content, if pre-RQE and RQE has similar H1 content, then probably we can say that quenching could have happened rapidly. Now we have to think about what kind of quenching mechanisms are responsible for rapid quenching. And similarly, from RQEs to post-RQEs, comparing their gas content can help us figure out what are the mechanisms that would be responsible for a sustained quenching mechanism for such long time. Because gas would like to collapse and form stars if the environment is conducive. And typically, if the region gas is hot, or the region around the gas is hot, eventually things will cool down and the environment will be conducive for star formation. But for that to stop, some mechanism should be there to constantly heat the environment so that gas never cools down. So yeah, so that's why having these populations as comparison in terms of the H1 content will help us constrain the quenching mechanism in RQEs. In total, we have 155 RQEs and 239 pre-RQEs and 301 post-RQEs as our sample, total of like around 695 galaxies, not around exact, and data. So now we have our sample ready. The next job is to get H1 data. What I did in the beginning was that, okay, I want the novel data, so I'll ask for the telescope time. I applied for telescope time several times, didn't get time because telescope data for elliptical galaxies, especially when you want to study H1 content, is very costly. For each galaxy, it can take about 10 hours. And that was the reason that I was not getting time. So I looked into the literature and checked like what all data I have. There are three kinds of data I found, H1 data I found for our sample. One was direct detection. It means that the galaxy has been observed by the radio telescope and we have the H1 mass information of these galaxies. Upper limit data. Upper limit are such data where galaxies have been observed by the telescope, but they didn't detect anything. So you have an upper limit, like how much max you can expect the galaxy to have gas. An indirect estimate is through you have the empirical data of other physical properties of the galaxies, and through that you extrapolate using some methods. Extrapolate the information that how much gas the galaxy would contain. So, so our H1 data included all these three types of data. And so in direct detection, unluckily, didn't find much. Only 4% of my sample has direct detections. And all the studies in which I found the detections have been mentioned here. And upper limits, so two of the biggest blind surveys are Alpha Alpha and FASI. Alpha Alpha is the Arecibo telescope that broke during the COVID time, and FASI is the 500-meter telescope in China. They both did blind survey of the sky and covered much of our sample. Basically, they have covered about 83% of our sample, and they are giving us an estimate like how much max we can expect our RQEs to have gas. And there are some overlap too. For some galaxies, we have data from both. And we found that FASI is about 2.5 times sensitive than alpha alpha data. So in that case, we used FASI data for our further analysis. And for indirect estimates, we found indirect estimates from Timorinia 2017 study. They used machine learning, basically artificial neural network, to derive gas fractions. They tested 15 different parameters and found that two parameters, particularly G minus R color of the galaxy and I band surface brightness of the galaxy, gives the best result with the least scatter of H1 gas fractions of the galaxy. What is gas fraction? Gas fraction is ratio of H1 mass to the stellar mass. And once you know the H1 gas fraction and you know the stellar mass of the galaxy, you can estimate what is the H1 mass of the galaxy. So for 94% of our sample, we have data, indirect data on our galaxies. Now the next question was whether to trust this data or not, to use it for further analysis or not. So I did some statistical analysis, root mean square, and used root mean square error and Pearson's R coefficient to figure out whether these data are trustable or not. And I matched the estimated T17 values with the actual alpha alpha detection. And I found that there is a strong correlation between the observed value and estimated value. So if root mean square is less and Pearson R is more, then that's a good thing. Like that means the correlation is genuine. And we are finding that about 83% correlation is there. So this this basically motivated us to go ahead and use the data for further analysis. So overall, out of 695 galaxies, except for 7, we have one kind of data or other for our sample. So I will be using, wherever I have H1 detections, I will be using that. And wherever I have upper limit values only, then I will be using upper limit values. But if I have the overlap between FASI and alpha alpha, then I will be using FASI because of better sensitivity. And wherever there is overlap between T17 values and upper limit values, I will be using T17 values if T17 values are lesser than the upper limit, because if they're more than upper limit, then they're of course wrong. And for those where only T17 values are there, then I will be using only T17 values. So now next, we have the data, we collected all the data. Now next step is check whether these galaxies have gas or not, because the case will be closed if it turns out there's no gas. Easy to say that quenching because no gas is there. But turns out gas is available. And in all these three data comparison for detections, upper limits, and estimated values, we see that for RQEs, we have only 2 detections. So we can say that either they have very less gas, similar like descendant samples, which we expect to not have any gas, or they have enough gas that they are matching the star forming counterparts. And upper limit is telling us that most of them have gas less than 25%. We don't know how much. And estimated value is telling us that it is most of them having gas between 10% to 25%. Anything about 10% is a significant amount of gas, and such gas should be good enough amount to form significant amount of stars in the galaxy. Did I not mute? Okay. So moving on, I just used H1 detection values and T17 values for further analysis, because upper limits won't give me any conclusive answer. It just gives me an upper limit. But detected values and estimated value, I can pinpoint that, okay, how much gas is there. So using those two values, when I compare the RQEs gas content with pre-RQEs and post-RQEs, turns out RQEs have similar gas like their star-forming counterparts, but not forming gas. So what's happening? And seeing the similar amount of gas, we could ask the question, is the quenching was a rapid one, that there was no exhaustion of gas and all of a sudden star formation stopped, or something else? So then we also found that not just gas is there, but gas is also more than we expect. So in this plot, gas fraction is compared over recent star formation activity. NUV minus R color tells how recently the star formation activity has happened in the galaxy, basically within past 100 million years. And based on these cuts, you can identify which galaxy would be in the star forming galaxy region or quenched region or green valley region. Green valley is a transitioning region where star forming galaxies, when going through the quenched phase, they pass through the green valley. Or sometimes some galaxies, they can accrete gas from its neighbors and start forming stars again. So they can go from quenched to green valley and eventually to star forming too. That's rare, but trivial cases going from star forming to quenched. So seeing here, most of the RQEs are transitioning galaxies lying in the green valley region, and they have more gas than the expectation. So what could be happening? They are quenched, but are they also in the process of accreting gas and eventually form stars? We don't know. So we'll have to study about their environment in detail later. So big thing, we found that RQEs have substantial H1 gas despite the quenched state. So now, what does this significant amount of gas presence and the quenched state reveal about their evolution? So next question was to figure out if we can say something about the evolutionary path, like how they would have evolved after comparing from the comparable subpopulations and knowing that they have gas. One way would be that we can distribute our sample between 3 emission types. So our sample has galaxies which has high emission regions like Aegean and Liner, or they don't have high emission regions. So I've distributed them in 3 samples, those with high emission regions and those with no high emission regions. What is Aegean? Aegean is a supermassive black hole at the center of the galaxy and emitting radiation, which can heat the gas and stop the star formation process. Liner is low ionized nuclear emission region in the galaxy. It could be all over the place in the galaxy. It could be near the center or spread all apart, like all over the galaxy. It could be, what is Liner? That's again is very debatable. It could be some very Asian radio mode that you cannot see in optical, and with a much weak power, and it's radiating energy which is heating the gas. Or it could be old stars called post-AGB stars spread all over the galaxy, and they're emitting ionized radiation, which is also heating the gas. So in this, we found that there's a striking difference. Galaxies in lower halo mass, like within 12.1, most of them appears to be having gas fraction about 70% or 17% or more. So kind of we can like debate that are the galaxies in the lower mass, those with higher gas fraction, are evolving differently those which are in higher mass and having less gas. So interesting thing is, in literature, any galaxies which is in the halo mass 12 or less, they can accrete gas easily, called through cold accretion mode, and form stars easily. We see that we have many galaxies in that region, and they have gas but not forming stars. So it's puzzling further, and in this journey, I'm trying to figure out more and more clues, like what really is happening. Next was, okay, let's compare their age and the star formation activity and see what we can find about their evolutionary track. So there is interesting observation. Ideally, if pre-RQEs, RQEs, and post-RQEs are evolutionarily related, then since RQEs have similar kind of gas as pre-RQEs, so we can say that, okay, from here to here, they would have evolved rapidly, like within a few 100 million years. And then from here, they could have gone steadily from recently quenched phase to quenched phase. So we should be seeing some galaxies here too, but there is a gap. So something weird is happening. Interestingly, those in the high emission regions, there is a continuous trend, and in AGN, there is not. So one speculation could be, okay, so AGN, all the galaxies can have AGN, but they can have episodic activity, like AGN could be quiet, not emitting anything, or AGN could be active and emitting radiation. So seeing this gap, I could say that probably AGN came first, and after the rapid quenching part, and they quickly heat the surrounding on the gas and stop star formation. And then liner came later, and then they were the mechanism, they sustained the mechanism for a long time. So that's why we can see a continuous trend here. So okay, for the emission regions, you can explain like that. But what about those without the emission regions? Well, one possibility could be that from here to here, after that, they probably went back to star forming. So you see then there were many in Green Valley. One possibility could be that some of them are in the process of accreting gas, and eventually that gas will cool down and they'll form stars again, and then quietly or passively evolve into the long quenched phase. So, and that will take like few billion years. So doing these analysis made us hypothesize that probably RQEs, all RQEs are not evolving the same way, and they probably are not quenched in the same way. And largely, there probably two evolutionary pathways are happening. One would be that RQEs rapidly quenched via major merger, and then those with the AGN or liner emissions, they took this path where they passively evolved to the long quenched galaxies. Others could be that some of them accreted the gas from its neighbor through the minor merger process, and eventually will start rejuvenating and start form stars again, and then passively evolve. So this was the conclusion of our H1 study. And next, I'll move on to the next part of my research, is about examining the environment of the galaxy, of RQEs. Why though? So one obvious reason is we could see that this can happen only if you are in an environment where you have neighbors around you to take gas from them. So I need to really check, are these galaxies which are centers of low density environment? So most of them are typically isolated, they don't have neighbors. But for this to be true, they have to have neighbors. So I'm like, okay, I'll study the environment in detail and figure out what really is happening. Other reason is to constrain the quenching mechanisms. There are two major quenching mechanisms, either intrinsic or environmental. Intrinsic is you don't have any environmental interaction. All the quenching is happening from within, some physical process, maybe AGN emitting radiation and heating the gas, or so many supernova explosion happened and that is also heating the gas, stellar winds, or the morphological quenching, which is basically the galaxy disk has been stabilized and the gas is not able to condense further, and that way there's just stop forming stars. And an environmental would be you have neighbors to interact with. Either you accrete gas from there, or you have massive neighbors, then they can take your gas, and that way you will stop forming stars. And third reason is that I really want to check that are because I'm calling them centrals and isolated because they have been classified like that in the past galaxy group catalogs. I need to check, are they really like, is there any error in their classification that they are centrals or they are isolators? Turns out, yes, there is some disparity. Yang 2007 Galaxy Group Catalog, their classification we have been using throughout. And they, according to them, all of our RQEs are central RQEs, and out of which 74 are isolated. By isolated, we mean, or in all these catalogs, isolated means the only galaxy of the group, and central is the most massive galaxy of the group. Again, another catalog, Galaxy Group catalog on these galaxies, they said that 86% of them are central, 65% isolated. Tinker 2021 says 94% are central, 76. So you get it, like there is disparity. So my next thing was, okay, to compare the environment, I need to have a unified criteria first. Like I need to figure out how to assess whether the galaxies are really central or not, or they are really isolated or not. So the questions I asked was, are the RQEs are truly centrals? Are central RQEs truly isolated? All these will matter in figuring out whether the quenching is primary, intrinsic, or environmental. Another thing is, are these RQEs pseudo-central? By pseudo-central, I mean they could be central of their own group, but they could also be infalling into a bigger cluster. And I'll explain that in detail. And if you're coming to an influence of a bigger cluster, that can also affect the star formation activity. So I need to check if a bigger cluster is also around these RQEs. And eventually, I want to quantify this environment and basically say that how isolated or how clustered these RQEs are. So starting with centrality verification. So I defined, based on some of the literature studies, that RQEs could be considered central if they don't have any neighbors around, don't have any massive neighbors than itself within the projected physical separation of 0.8 megaparsec and within the line of sight velocity of 250 kilometer per second. So in a 3D space, I'm measuring all around, like in a region around me. I'm checking that if there exists within this region, if there exists a massive galaxy more than me, then I'm not a central galaxy. And yeah, and if there is one, then these RQEs are classified as, I'm calling them potentially misidentified centrals, because they could be probably a satellite revolving around the bigger massive galaxy that I found within this vicinity, 0.8 megaparsec and 250 kilometer per second. Turns out, yep, not all of our central RQEs were centrals. Only about 85% of them were true centrals, and about 15% were misidentified centrals. That is, we found massive neighbors around those galaxies in a close vicinity. And also this error rate kind of aligns with the error rate in their classification. Another study had showed that Yang catalog has about, when it comes to classifying the low mass halos, they have error rate of about 25%, and this is comparable. And next was, okay, centrality is, we have our definition for centrality. Now next, and I've already figured out how many are really centrals and how many are potentially satellites. Next was to check, are these true centrals are really isolated or not? Why? Because if they're not isolated, then they could have potential environmental interaction, and that can affect the star formation activity. So there are tons of studies about how galaxies could be classified as isolated galaxy in the literature. 3 particular studies, AF15, B15, and Wang 2014, they studied similar galaxies like ours, and they defined isolation. And even in each of their definition, there is only 16% agreement that whether they are isolated or not. And if I include the Y07 classification too, only 30% agreement. So again, that was my motivation. Okay, figure out a unified way to identify whether these galaxies are isolated or not. So my criteria was, I'll take the projected physical separation, line of sight separation, as well as the mass ratio. By mass ratio, I mean, I want to see if there is, for the centrals, if there is influential neighbors around me or not. By influential, I mean any galaxy which are lower mass than me, but at least 1/10 mass. So anything lower than the 1/10 mass is not an influential neighbor. Anything within my mass and 1/10 has the potential to impact the star formation activity. And they could have enough gas for me to take away from them and start my own star forming process. So I looked for such influential neighbors. And if influential neighbor was found for the true centrals, then I'm calling those as non-isolated galaxies. So it turns out about 16.7% are non-isolated, but majorly are isolated. So you can say that majorly RQEs go through intrinsic quenching mechanism, and those which are non-isolated, some kind of interaction is happening. What kind of interaction is happening? We'll discuss that later. And I also, in this plot, I'm showing that how far the neighbors are, influential neighbors, and how massive they are in compared to RQE's mass. And in this plot, I speculate that these candidates, which are comparatively lower mass and very close to RQEs, are the candidates from which RQE can easily snatch their gas because they are less massive and also very close. So these would be the one could be probably involved in RQEs, those we show H1 surplus. So this could be the galaxies which would be saying that, I'm goofing up here. I'm trying to say that these galaxies will be the one responsible for observation of extra gas in RQEs. Then next step was to figure out if the RQEs are pseudocentral or not. So pseudocentral means they are central of their own group, but they are coming within the influence of a bigger cluster. Bigger cluster really means greater than 10 power 14 solar mass. And even if you are at the periphery, you are under the influence, and you might appear an isolated central galaxy of your own group, but the medium, the intergalactic medium or intracluster medium of the big cluster can affect your environment. And in the process of you falling to the bigger cluster, either your gas would, because of ram pressure stripping, your gas could be further removed from the group itself as you are further and further going towards the center of the cluster, and that can stop star formation. And I found that only one RQE is classified as pseudocentral. So even though there are these two are within the influential zones, this is also pretty close. But again, 13.7, 13.9, 13.8 is not that massive. And turns out all these fours were anyway already classified as misidentified centrals, so potentially satellites. So they already have a bigger galaxy close by to worry about rather than a bigger pseudocentral. So in a nutshell, There's only one pseudo-central, and that could mean that RQEs are, again, are not influenced by any cluster activity. They are in a relatively low density environment. Next was, okay, now I want to quantify the environment and see what that can tell us about quenching. So there are various ways of quantifying environment. We followed the fixed aperture approach from the literature, in which you already define a region, and in that region you figure out what is the number density of the galaxies and also what is the stellar mass density. Number density includes all the galaxies including RQEs, and surface stellar mass density includes mass of all those RQEs, all those galaxies including RQEs within that region. So number density will tell us basically how clustered galaxies are, and surface mass density will tell that how dense the environment is in terms of mass. And we found that most out of 155 centrals, about like 50% or 47% are truly isolated. There is no neighbor. So sure shot, you can say intrinsic quenching mechanism happening. We'll discuss later what kind of intrinsic quenching mechanism. And for rest of the sample, they can be classified into these 4 quadrants. And those quadrants are regions with higher mass neighbors or lower mass neighbors, or region with more number of neighbors or less number of neighbors. So this would be, you have more neighbors as well as you have massive neighbors. So this will be a very dense environment, and their quenching could be primarily environmental. Here you have many neighbors, but they are like very small, so probably not much influential. So in this case, you could be quenched intrinsically, but also you could be probably accreting gas from them. And this is the environment in which you have very few neighbors, but they are massive. So some kind of environmental interaction can happen here too. And in this one, you have very few neighbors, and whatever neighbors you have are like very, very less massive, significantly less massive. So you can, even in this region, you can say that the quenching could be primarily intrinsic. So this plot basically tells us that RQEs can be majorly divided into 2 regimes: intrinsic quenching regime and environmental interaction regime. And 70% are in intrinsic and environmental. Within intrinsic, we have some populations that have AGN and some no AGN. And here, when I'm saying AGN, I'm including both AGN and liner sample together, because I'm trying to say high emission regions. And then similarly, within the environmental regime, non-isolated true central will come, and the misidentified central, which are potentially satellites. And within them, how many have AGN, non-AGN? This is just statistics about that, and we'll discuss further that why I have separated into these. So we'll see that in this plot, I plotted all these RQEs class based on the environmental studies, and primarily the intrinsic ones. There are AGN sample, non-AGN sample, then misidentified central, there is AGN and non-AGN sample, and then non-isolated true centrals, that is, they have influential neighbor around it, AGN and non-AGN sample. What does this tell us? Tells us that these misidentified centrals, this one with AGN have maximum gas fraction, non-isolated ones have very few gas fraction, and these have significant gas fraction, about 10%. So right away, the ones with AGN, we can say that, okay, it's easy to explain AGN is radiating energy, and that is heating the gas. And because gas is hot, so they could be quenched. What about others? Well, it's these ones which are truly intrinsic, that is like truly isolated and have no AGN. How do you explain so much of gas in that and still they are quenched? One possibility is that gas is just diffuse. For star formation to happen, gas also has to be dense, about 10 to the power 20 atoms per centimeter square or more. So enough gas is there, but somehow they're diffuse, and because of that, they are not forming stars. For this one, misidentified central with non-Asian, we can say that they are potentially satellites and probably going through satellite quenching mechanisms. So what is satellite quenching mechanism? A smaller galaxy, satellites, when it revolves around a bigger one, because of the gravitational interaction, this bigger one shreds their gas apart, and that way they lose their gas and stop forming stars. So that could be happening in these. In these ones with Asian, both could be happening, environmental as well as intrinsic. Asian could be responsible for heating the gas and quenching, but at the same time, probably their gas is also getting shredded away from them because of presence of a other massive galaxy nearby. What about this one? Non-isolated true centrals, which have influential neighbor around it, but they have very less gas. Probably the simple explanation would be there's not enough gas, so just died out of exhaustion. Or at the same time, it could also be happening that they are in the process of accreting gas, like the neighbors are there, but in our study, we still don't see how much gas they have accreted, and it requires further detailed observation. So we have narrowed down from intrinsic to environmental, narrowed down to what kind of specific quenching mechanisms could have been taking place in these RQE classes. So big takeaways is for the both astronomy part of research is that RQEs have gas. So simple explanation that just gas is not there, that's why they're dead, is out. And they are not necessarily all of them are evolving in the same way. Some are probably accreting gas, some are quenched due to heating mechanisms, some are quenched due to diffuse, some are passively evolving, or some are probably in the path of resonation. And most of the RQEs are indeed isolated, and so intrinsic quenching mechanism is the primary mechanism responsible. And then a very few RQEs are not really centrals, they are potentially satellites. And because of that, they are easy to explain, they're going through satellite quenching mechanism. Now, astro part is done, and moving to my co-discipline part, which is curriculum and instruction. And I will be talking about research I did in that area, which was like I developed a introductory undergraduate radio astronomy course, which is not the norm. Typically, the course is taught at grad level. So why? So my own personal experience was when in my undergrad, I was whenever I did any RU types of internships, it was always in optical astronomy. And optical astronomy looked fascinating because you see fancy galaxy images and you get attracted. After my undergrad, someone gave me a chance to do research in radio astronomy, and I was never interested because you just cannot see it directly, it's all indirect. But when I delve into the research, I found out that it's pretty interesting, and the galaxy that you see, we could have never imagined. It could look like anything. It could look like weird shapes, some animal shape or anything. And it doesn't look like galaxies. And that was very interesting for me. And the process itself, how all the technicalities that go, how we from like indirectly from the data, how we get the image is very interesting. So I was late to explore this field, else probably I would have directly went into research in this area or shown much interest into this area within my undergrad itself. And also big, huge 1,000-kilometer distance telescopes are being built in South Africa and Australia called SK. Already we have tons of radio data that is unused, so much archival data. And with this big telescope, there will be even more. And since radio astronomy is not typically taught at undergrad level, students usually don't know about this field. So when they apply for PhD program in astronomy, often the direct interest is optical astronomy. We want to bridge that gap and have students exposure to this area as well, so that we have more students in the radio astronomy research area and they can carry on the research in that area. What makes me expert to develop this course? Well, I have some experience as a radio astronomer myself. Before coming here, I had done 4.5 years of research in radio astronomy and published paper in that area too. So I understand the field, and I have tons of ample teaching experience here at UMKC, teaching physics, and also my coursework in curriculum instruction helped me become a better teacher, and the Preparing Future Faculty program also prepares you how to teach at the college level. So I've done all those, and I have the credibility. And also, I want this, radio astronomy typically is taught at grad level because it's hard. It involves complex concepts, complex maths. To bring it to undergrad level, I will have to really tone it down. And I did that when I was teaching at Rockhurst as an adjunct faculty. I was teaching to the health science students, physics, and I had to design experiments in a way which is like easily understandable in their field, in health sciences field, and without using calculus or much of complex math, I had to explain. So it was fun designing all that. ChatGPT definitely helped me a lot in guiding my own instruction. So I had the experience of toning things down, making things easier. So I'm like, okay, I will be able to do it and bring it to the undergrad level, this Astro course. And my curriculum instruction expertise basically gave me introduction to some of these frameworks that I have used in my own in my research of developing this course. One is Bloom's taxonomy, which says that you got to scaffold students and start with big picture first and then go down to the details. I've used understanding by design framework. Basically, you want to have first expectations, what really you want to get out of the class, and then once the objective is set, then you design your instructional strategies. Concept-based learning, I want to focus most on the learning of the concepts rather than the rote memory of everything. And then, of course, the teacher's craft, 10 essential skills of effective teaching. I read that book and I've used some of their suggestions that teaching is effective, students learn better when the assignments are more of formative and if the teacher interacts with the students more. So first thing was to set up an expectation. What do you want out of this course? Well, I want the students to explain all the physical processes of radio related to radio emission or anything in the radio astronomy pretty well at the end of the course. They would also be able to not just learn the concepts, but also be able to learn what typically a radio astronomer do as a astronomer, like data analysis in radio astronomy. It's not trivial like optical astronomy. So I want to introduce to them that area too. So in the end, basically they will be ready with confidence and competence that they can start a radio astronomy project by themselves. They can take the archival data and start doing further analysis. So that's the end goal. So this is like, I will be talking briefly about this course as I'm running in time as well. So what I am giving in this course, basically complete blueprint of the course. I will be providing syllabus, detailed weekly content, like what all each lecture should be taught, how it should be taught. Again, it's subjective. Like I would like to teach that way, a sample lesson plan, how assessment should be done, and sample assignments and grading rubric. So key takeaways, like what you should take away is that course is divided into two parts. First half of the semester, foundational knowledge will be taught, and second half will be on technical proficiency. That student will learn how to understand the radio data, how to extract information out of it, and feel like what a radio astronomer does. Classes will be typically interactive and it will involve active learning. It is broken into 15 minutes, 45, 15. Each class is 1.5 hours. I will discuss a detail in further slides. And assessment strategy is like how basically they will be assessed. I don't want the students to worry about grades more and always like, oh, I got 100. I want to eliminate that and focus more on learning and have fun in learning. And also how they will be evaluated is the key takeaway from this course that I'm developing. So introduction, so lectures would be introduction slides, lecture slides, and conclusion slides. introduction would be that you want the students to like have first icebreaker moments. So one of the icebreaker moment I have stolen from Professor Candace is that once you have the objective setup for each class, that what you want students to learn, ask students about each of the objective to answer on a Mentimeter app quickly. And they don't have to answer in like, do you, yes or no. They will just explain in terms of, yeah, I feel confident explaining this. I've seen this. So basically, questions like this or answering in this way doesn't make students feel a little ashamed that, oh, I don't know something, like I'm always clicking no. So we don't want students to have that. And basically, we want them to look forward to knowing the answer. And then in lecture slides, lecture will be not just trivial session in which just giving lecture like how I'm giving lectures. It would be that students would be interacting with the course content. So at least we'll have 3 active learning strategies. One example is think, pair, share. The students will collaborate within themselves and share answers related to a particular question the teacher will be asking. They can have discussions, some mini activity. So you can think of many ways how to involve students more in the process of teaching. That's how they will learn. And then at the end, they will have some conclusion slides. Basically, the same question that was asked in the beginning, it will be asked in the end, and then they will be discussing that again within themselves, within the groups. You can, again, this is Libby's idea, pair them in groups randomly, and every time they could be in a different group. And then they can share they can educate each other. Like you can assign questions to each of the groups and they can answer to the other group. And as an instruction, I will be just the one who will be invigilating their explanation. And if there is a misunderstanding, right away then and there, I can clarify that. And after that is done, students will go home with some exit ticket. This is stolen from Professor Barger's idea, that you ask 2 questions to them that they can answer in the Canvas, that what they like what is something that is still unclear from the today's session, and what they learned today that they can explain pretty well. This helps students reflect on their learning, and reflection is key, one of the key ingredients, if you want to say, for the better understanding of students. And this complete process, this way of teaching, in this way of teaching, there is assessment is happening during the teaching process itself, and active feedback is being given to the students. So it is rare for them to take home a misunderstood concepts. Again, so assessment would be 2 types. One is one on concept discussion, and another is data analysis project. Briefly, what the one-on-one concept discussion would be, that as an instructor, I will be providing them some of the key questions or key conceptual questions for which they really need to know the answer. Like they really need to understand those concepts. They will know that in advance, and they have to submit the answer to that before we meet for the one-on-one discussion. And when we are meeting with one-on-one discussion, again, this class is for short class, I should mention, like less than 20 students. You cannot do with 200. And when the student comes, they are supposed to explain those answers to you. And during the explanation, you will be able to figure out then and there itself if there is a gap in the student's understanding, if they have misunderstood something, and then you will clarify there itself. And once the clarification is done, students are supposed to resubmit their homework again. And evaluation is basically the students are starting with, evaluation is students are starting with 100% grade. So they don't have to worry about, oh, you have not put the grade, it's showing 70%, like it's starting with 100%. The only way to lose 100% is, despite so much support, you are just not taking the support and not working on it. You being graded on your effort to improve. Right away, the students probably will not do that good because they don't know the stuff pretty well. But as they are learning, they'll learn more and more, understand better. they start improving. And as a teacher, I want to see who is putting effort, and they will be graded according to that. And then I'll just mention that there is similarly like that, there is data analysis project in which a 3-hour session would be there in the end once they have learned about how to do all the data analysis during the coursework itself. In the end, in this assignment, when everyone is working on their data analysis project, me as an instructor, I'll just ask questions. I will be observing them, and I can ask simple questions. Why did you do something? Explain your approach or justify your decision. And then and there, if I get the wrong answer, I'll clarify there. Like, I'm not there to judge and give them, okay, wrong, 0 mark. No, I want to help you there and basically make them feel that you are really taken care of. Like, I really care about you and your learning, and I don't want to punish you. So I want students to not have that feeling that they will be punished. Big takeaways. This is basically a course map, how a complex radio astronomy course can be taken from grad level to bring it to undergrad level and still taught necessary stuffs that will help them. If someone gets interested in radio astronomy, go and jump into that area of research. Also presents a template which can be applied to other complex physics courses or mathematics courses, how you can tone down to undergrad level. And then unique approaches of teaching and assessment, which is just a food for thought. It's an experiment phase. I've never tried, but I would love to try if I get to teach. And teaching is a feedback, continuous feedback process. Like every year you'll teach that. If you teach the same course, based on the feedback, you'll do something different, you'll do something better. And in the end, so co-decision part is done. I have, from my astronomy part, I have submitted my current research and it is yet to be published. It is under review. And one other paper is being written and it will be submitted soon. From co-disciplinary part, I have done lots of work. I have my Rockhurst experience teaching at college level was taking things from my curriculum instruction and applying there. And also I have worked with Professor Schlein, Professor Candace, and written a chapter on active learning strategies using ChatGPT, and that is also in press. And then I have some co-authors with other researchers in related to the research I did during this time, but not majorly part of my dissertation. All the codes that is part of my research will be published on GitHub so that things could be recreated, and all the catalogs, the value-added catalogs that were produced during this research will be on Vizier catalog, on Vizier website. Vizier is a place in astronomy where you dump all the catalogs for others to use. I've given several presentations here or conference virtually or in person. These are just the list of that, some of those. Future work could be that, yes, we are limited with the H1 data, but to have much clearer understanding would be to have a better resolved H1 data of these galaxies from the telescopes, which would be spatially as well as spectrally resolved. One can say that, like in this, these three galaxies, just by seeing this, it's hard to say that they're interacting. But if you see in the radio in H1, you can clearly see that from the smaller galaxies, gas is being taken away by this bigger galaxy. So this information is missing. If we have a pretty resolved study on these RQEs from the future telescope that is upcoming, SK or NGVLA, we can probably narrow down the quenching mechanism and understand gas content even further, much better, and probably understand the evolution of galaxies in low density environment even better than what we know at the moment. Not just H1 observation, but radio continuum observation of these galaxies could also be helpful, because even though from our earlier observation, even though some of those RQEs are non-agent type, they could be, if you observe in radio continuum, some of them could appear Asian, just a very weak Asian emitting in radio wavelengths could be there. So it's important to figure out if this is there, because this is there, then this can also heat the environment and stop star formation. And for the co-discipline research would be, next step would be to go and teach that course. Someone can just take the template and apply that in their, if they want to teach radio astronomy at undergrad level, they will have to create all the lesson plans. At the moment, I have just added one sample lesson plan. Another research would be, since it's a Gen AI era, we need to really think about how each of the, how a course with Gen AI adaptable. Basically, Gen AI should be used by students in helping in their learning process rather than a tool for cheating. So at the end, I'm done with research talk, and I want to acknowledge some of the people that are important in my PhD time and in life. First, I would want to thank all my committee members, all my advisors. Professor Ulis has been really, really helpful, kind. All my co-discipline supervisors, Professor Schlein and Professor Barger, always available despite being so busy. Whenever I ask for help, any co-discipline discussion, within 24 to 48 hours, they have always replied me and very kind. Professor Libby, right from the beginning, even though she has been recently added as my academic advisor, she has always been there as my lab instructor, lab supervisor. So I have worked with her since beginning, and she has been always very kind to me and very helpful. Professor McIntosh is the one who gave me the opportunity, and I'm thankful for all the experience I had under him. It really made me grow as a person as well as a researcher. Professor Kale is my external astronomy advisor from India, and she has been instrumental in my research experience in almost past 10 years. She, under her, I published my first paper in radio astronomy, and not just in academic area, even in my personal life, she has helped me a lot, especially when I was going through terrible sickness related to my intestine. She gave me some information that healed me. And another collaborator, Dr. Sravni, she has been a big collaborator in my research and also has helped me in dark times and very supportive, always available. Professor Chaudhary is our department division head and always ready to help students. As a grad student, whenever I needed help, he was there and he helped me. So I'm thankful to all these advisors. Of course, I have to thank, now that I've thanked my advisor, I have to thank all my loved ones, my mom and dad. Because of them, I'm here, literally. And my sisters, my niece, and my sister's husband. My sister's husband is basically the son that is not there in person in India. And my sister is a key ingredient part of the family, which is always like, no one really gives enough credit that she needs, that she should be given. So that kind of identity she is there in the family. Mom and dad, I miss food from mom, and dad is just a very curious, interested guy and super proud dad always. And my niece is born Chiefs fan. And she's the reason the happiness in the family has increased a lot. And she's the reason that my parents don't bother me about when are you getting married. So, because they're busy with her. And of course, I have a family of about two. Some of them are here. Grandma Matthews, Emily, and Emily's dad. Right from when I met Emily, their family, from the very beginning, have taken me into their family and are very inclusive and very kind and always showered so much love. And also two family members are two dogs, Daisy and Puddles. Daisy is no more, and Puddles is just a pain. He is just a constant bugger. But they make my life easy because most of the time I work from home, Emily's at work, and this dog keeps me company and keeps me stress-free. And my family, all my friends who have come here, they are my family. Basically, I call them my friends and family. And right from the beginning, 2018 August, when I came here, very key part of my life in several areas. I don't want to take enough time and say personally how they have helped me here and there, but big thanks to Jamie, M, and Debbie. They have been involved in my life a lot. And Mohan, I forgot, who's not here because probably he forgot that I'm giving talk. And there are several other friends that I'll probably forget. So I have names of them if they're watching, and photos of them. My pastime is playing pickleball, and some of the folks, when I get distressed, my distressing is go play something. And I even won the championship here at UMKC. So I'm a pickleball champion too. And in the end, I'll give special thanks to my girlfriend, Emily. She has been there with me all the time, in thin and thick, very supportive. And Jamie, key factor that I'm giving talk here, and Professor Rulis and Professor Kale, who have been agreed to help me graduate. So yeah, and in the end, I'll also thank Extra Slides. No, I'm just kidding. Thank you. Thank you. Let me see if, yeah, so floor is open for the questions. Maybe Professor Rulis wants to say. Yeah, thank you.
All right. Thank you very much. Excellent, very detailed and interesting presentation. I like it a lot.
Thank you.
I've seen it one time before. I saw it. I knew it was coming when you did your practice. But I want to open the floor now for questions from the audience. And online too.
Yeah, Debbie, can you keep a track of the questions and let me know later? Yeah. Okay. Thank you, Preston.
Oh, great. Go ahead.
Yeah, go ahead.
I'll try to repeat the question once you do. So don't make it too complicated, because otherwise I'll have to like remember everything. And
really great talk. Amazing work.
Thank you.
Really quick question, and I'm going to ask a very technical question.
That's fine.
On one of your slides, you mentioned, again, this is regarding the astro-related talk. You don't have to go back to that
fine.
slide. It's okay.
Okay.
You mentioned that for the RQEs, you were looking at how many other, if they have any neighbors, so to speak.
Are you talking about the influential neighbors?
Influential neighbors,
Okay.
yes. And you found that majority of the RQs are actually 80%-ish or so do not have any sort of, they're isolated, true isolated.
Yeah, 70% doesn't have influential neighbors.
Yes.
Yeah.
And 25-ish
Yeah.
percent do.
Yeah.
I was wondering, because you showed a really nice quadrant of things that can potentially go from pre-RQEs to RQEs, and one of the major contributions could be major mergers.
Yeah.
So when a merger happens, and if RQEs are preferentially likely to happen when the merger has happened, then you would not expect another companion to be nearby or influential companion to be nearby. What are your thoughts on that?
Yeah,
so just to quickly reiterate the question, summarize, the essential element is that the RQEs, by some of the presentation earlier, tend to not have a lot of influential neighbors. Statistically, they don't. Yet at the same time, they have formation due to mergers. And if you are being formed due to a merger, wouldn't that imply that there's some kind of influential neighbor nearby?
Yeah, so one could be that like major merger is one of the easy and obvious explanation, because elliptical galaxies in low density environments typically formed through major merger. But then there is another morphological quenching too. So you don't have to have any galaxy around it, and just by itself the disk can stabilize, and through that also quenching can happen. So that could be the galaxy RQEs could be the one with influential neighbors and have not gone through major merger, probably have quenched through morphological quenching and have influential neighbors now, from which they can like accrete gas later and go to rejuvenation phase. Oops, sorry. What do you think? Like, I think that could be.
To me, the morphological quenching idea never really stuck with me.
I know.
It sounds like if you build a city, you stop building new buildings, is how the argument goes. So the analogy for morphological quenching is you turn into a specific shape and you stop producing stars. That never made sense to me, because it's like saying, oh, you build a city, you're trying to grow a city, you're forming new stars. You build a city of the size of Kansas City, and all of a sudden you stop building new houses. That didn't make sense, or at least the arguments were that were presented in many papers.
Yeah.
oh, all of a sudden you are now this shape, so stop forming stars.
Yeah.
So that doesn't make physical sense to me, but it
I-
could be correlative or not causative.
Yep.
Is what I think you're trying to say.
Yeah. And I don't know if in simulations, do you see morphological quenching happening? I have not seen. Yeah, that paper, it does get so many citations, but there is not much study like others have studied morphological quenching, but people do cite.
Great.
Yeah, Jamie, go ahead. Uh-huh. So future observation. So right now yeah, go ahead.
Can you
Oh,
repeat
yes, sorry.
Oh, yeah. I didn't catch entirely. Go ahead and say it one more time. Yeah. So how future observations constrain that,
Yeah.
and also the gas kind of star formation.
So so right now, only information we have is H1 mass, because the whatever data we had is not spatially or spectrally resolved. So future observation would be, you want to let's say this is the size of the galaxy, and all the H1 content in the galaxy is around this area. So spatially and spectrally resolved would be that you want at different places the observation of H1 gas in the galaxy, and within the spectra also, like very fine within let's say within 20 kilometer per seconds of the spectra, how the gas is varying. What this will do is, it will help us figure out first that is gas all around in the galaxy or concentrated to a certain region. It will also help us figure out if the gas is, what is the kinematics of the gas? Like, is it gas flowing towards the center or going out? If you're flowing towards the center, that is like you are moving towards the process of star formation. If going away, then you can say that, oh, there is some kind of mechanism happening near the center of the galaxy that is pushing the gas out. So we'll be able to know that for detail. And temperature of the gas also, so that will also help. Like if the gas is really hot, column density of the gas. Are gas really diffuse? You'll know from the observation that is it less than 10 to the power 20 atoms per centimeter square. So all these is dependent on spatially and spectrally resolved data. So that would go on. And next was, what was the other question? Okay.
So the star, the history of
Star forming. Well, it's all correlated. Yeah. Uh-huh. Mhm. Mhm. Well, unlimited data to study these galaxies. Well, then, so big question is that why they're quenched, right? When they're supposed to be not quenching, because they're in an environment where star formation should be happening easily. So not just looking H1, I would look for H2. Basically, I will be looking for CO emissions, because CO emissions will tell us that exactly like what kind of gas has been converted into H2 to form stars. And the difference between H1 and the H2 content can really tell us that how much is really have been converted into forming stars. So that will be a very key information in understanding the evolution. And the more I'm able to explain the quenching in this, I will be able to add to the field that how the evolution is happening in low density environment. Currently we know that, okay, in high density environment, central galaxy, because of the clustered and hot medium, it's gonna be dead. There's no star formation happening. And we know in low density environment, field galaxies, dwarf or small groups, gas will easily fall in and it will condense and the star formation will happen. But clearly there is a gap, right? So I will be adding, the more I know about RQE status, I will be adding the gap and probably will be able to tell that no, in the low density environment, there are multiple ways a galaxy evolves. And so that will increase our understanding of galaxy evolution in whole. I don't know, did I add it? Did I? Okay. But I won't observe. I love Asian more. Thank you. It was a beta. Thank you, Jamie. Cyrus.
Yeah, sorry.
Yeah, so as I was saying, the continuum radio emission, not just H1, because that would change the game. If turns out, right now about 20% have AGN, right? And if they have radio mode AGN, let's say 50% of them, then like different kinds of AGN, but still AGN are probably the primary factor. And intrinsic would be like, we already know majorly are quenching through intrinsically, but we can pinpoint like what all different ways. So yeah, I would like to look at continuum emission as well. And of course, the H1 emission, so that I can see the interactions, because in optical, if any interaction has happened, optical emissions dies down quickly compared to radio emissions. Radio emission will take about 1 billion years to die. So since these are caught in the act of quenching, recently whatever has happened has happened. So if you observe them, any interaction that has happened, we can like see that in H1 observation. And as M was asking, okay, merger has happened, how do you expect a neighbor to know? All this can be answered clearly, right? So yeah, H1 and radio continuum. Debbie? Okay, do you want to go ahead? Oh, he wants to. Okay. I think he cannot unmute himself. Ben, can you hear me?
Yeah, Dio. Can you
Sorry, I
hear?
forgot to send you the link.
Yeah. No, I would just like to say, amazing talk. It's a great research that you've done here. I do have a couple very quick questions on this. How did you, when you're classifying your galaxies as AGN or liners, how are you doing that?
Through BPD diagram.
Okay.
Yeah.
And then I guess kind of as a follow-up, is that using the existing like Sloan spectra? So would it be helpful if you had the DESI spectrum, DESI spectra over these galaxies to kind of at least maybe enhance the sample, be able to get some of the other galaxy properties from them from the like the DESI spectra, as well as like maybe morphology from like either Legacy or Euclid in the as it passes and does the wide survey?
Yeah, so I already used the from like DESI, the decals images, which are, since decals is more sensitive than SDSS, right? So through comparing their images, my sample was not 695 that I have. I had a bigger sample. So in decals, turned out that some of them were spiral looking. So they were not really elliptical. So I had to remove that. So yeah, you can say that like if the more resolved, better image we have, probably some of them are peculiar ellipticals and not really that boring spheroid. And spectra, yeah, I don't know what else more I can add. Maybe I can refine on the BPT diagram and probably get a better read on liners or AGNs. That would be the improvement. Yeah.
I mean, incorporating multiple different like diagnostics would probably be something that would be an interesting kind of enhancement of like, you know, BPT, but some of the other like emission line diagnostics in addition. be interesting.
Yeah, and comparing the spectra from central region and outside region, like that can help us, like whether major merger was a really factor or not. I tried all those in the beginning, but didn't have enough data, so let it go. Okay, Ben.
Great. Additional questions from anyone? Yeah. please.
Emily. Thank you, Em. Uh-huh. Wow, really good question. So one would be direct imaging in that itself, like I had shown in this direct imaging. One would be the way to tell, and what else? Yeah, indirectly, like I had shown in the plot where H1 surplus, I was showing that these gas have more H1 than expected. Indirectly from there, you can say that the ones in the Green Valley region with more gas than expected could be the one accreting gas. Also, the environmental study, like you seeing the neighbors are there, and that will help us cement that, yeah, there is some candidate from whom you can steal the gas. So these are, image is the one that is coming in mind, and spectra, I don't know how through spectra. Yeah, I don't know. Image would be the easiest way to do it. Yeah.
Great. Other questions? Online or the audience? One more. Yeah, great.
So you had some big takeaways.
Yeah.
First one, that
I'm
there's
not
more
using-
H1 and these might be expected.
Yeah.
Is that new to the field, or did this study kind of cement that idea more, or is that kind of a new study?
So-
That seems like a big.
Yeah, so in general, if you say elliptical galaxy, then means most of the time it means that, yeah, they are dead galaxy, they are not forming stars, and so not forming stars would mean that they have consumed on their H1 gas, so they won't have much. But seeing them having gas is not that puzzling. Puzzling is that they're not forming stars, despite being in an environment where they should be. So that is a bigger puzzling part. And of course, finding out that they have more gas than expected, and as I've discussed, it could be due to various reasons. It is, to me, it's not that much of a big deal or question, because our data is very limited. Let's say, because any neighbors that I'm finding, it's all within the sensitivity limits of the telescope. If you further resolve telescope, you might find even more neighbors that is not being observed now. So, so I would say that for me, the most striking part was not forming stars. Yeah, again.
Yes, please.
Hubble telescope will clear out to these galaxies. Are the telescopes that y'all use are highly, can you describe it?
Yeah, so my data is from different telescopes, and there is, like, Hubble telescope data was also used, but it's not part of my, I have not added here because I didn't get any significant information from Hubble telescope data, but Hubble telescope data was used. There are data, other ground-based observatories, they're all over the world. Those have been used, and not just the optical telescope. Like Hubble is an optical telescope, which means that you get what you see, kind of like how you're seeing through eye. I've also used data from telescopes, which take data from other wavelengths that our eyes cannot see. And I've used those data too, and they are in the sky, like Galaxy is one telescope, which is one of the NASA telescope. Then I've used the information from different radio telescopes all over the world. Radio telescopes, they look like a mesh antenna, They don't look like having a mirror or a lens. So information from that has also been used. So that's why it's a multi-wavelength study, I call it, because information from optical, UV, radio, all three are there.
Additional questions or follow-ups? Jamie,
Jamie.
yes. Favorite moment from the teaching?
Teaching itself. I mean, teaching here at UMKC, like, yeah, I really love, especially when I was teaching the physics mechanics lab compared to the electrodynamics lab. Mechanics lab is where people really do things and get the output, right? Compared to electronics lab is like black box. So my students, most of them are like freshmen, sophomore, and some of them don't come from physics background. So me toning down and explaining them and seeing the aha moment in them when they finally get it, oh, I loved it. So my 2 hours was like, it will go like this. I will go to every table, talk to every student. So interacting with them was the like best moment of teaching. And also when I taught at Rockhurst, it was an interesting experience because I was teaching completely non-physics background and I just cannot use any normal mathematics expression. And I had to really think that, okay, how do I, and then I also had to give example how it sets up in the medical field. So that was fun. Yeah. Creating this radio astronomy course, I think the way I want to teach, if I get to teach like that, that would be an interesting one. Maybe Libby, you can experiment. I'm enjoying making solutions for Libby too in cosmology. Yeah. Thank you for asking. Oh,
Yeah, we'll shift to the committee interview here. Unless there's any other questions.
let me see if Debbie, is there any?
Okay, great.
Should I ask Candice if she has?
Oh, well,
Maybe in the later.
yeah, we'll
Okay.
do that.
Okay.
Great. All right. Thank you very much. All right. So now we'll excuse the audience for a little bit and we'll have the committee members do an interview. Ask questions.
No, I should show the group. Thank you all for coming. And Debbie, thank you for helping with setting up all the thing. I should maybe.
What I'll do is I'm going to pull this microphone over here. Do you think that'll work? Yeah, let's do.
Professor Barger and Candice, can you hear me?
Yes. Yes.
Okay.
Geometry is a little awkward.
question.
Not quite
Good
far
for
enough.
that.
There you go. That'll work.
Okay.
Should I?
All right, so we'll just kind of go round robin here real quick.
Okay.
Typically we'll have the
Wait, please.
co-discipline start first with questions and then work our way around.
Yeah, I guess randomly people are popping.
All right, yeah, so Candace, you had your hand up there, so why don't you go ahead and start?
Sure, and I'm sorry that people left for what I want to say, so it wasn't a question so much as I just wanted
Oh,
to
I'm sorry.
say to Dio how incredibly proud I was at the level that he integrated his co-discipline into his thinking and his work. You know, you really took your interest in teaching and merged it so well with your interest in astrophysics, and I was just really proud to see how that all culminated in preparing documents for teaching. And I just wanted to recognize your enthusiasm and your efforts in that domain. So I'm sorry that the rest of the attendees did not get to hear my comment. I truly think you should be lauded for that. I know from so many conversations that this wasn't just a hoop that you jumped through. You really took your teaching very seriously and you were very enthusiastic about it.
I totally
Thank you,
agree.
Candace. Oh, what, Professor Baga?
Rita, did you say something?
I just said that I totally agreed with what
Okay.
Candace said.
Thank you, thank you.
I'm sorry, I didn't pull you in. I just kind of was confused about the hand raise there. It was my fault. Oh, but one thing really quick, are you still recording?
Oh, yeah, I should stop it.
Great, okay, so that comment got recorded, so that's great.
Yeah.
So I think we'll stop the
That's
recording
good.
here. Yeah.
Thank you for making sure that I still want to start with it.